So far we've learned, all right, if I were to ask you on the test a week from today, all right, how would you describe current to me? Flow of electrons, movement of charge, all right? That we have to have moving charge, okay? And remember, all right, when we talk about electricity in this room right now, it's a lot easier to move electrons than protons. So most of the time, the vast majority of the time, we're talking about moving electrons, okay? Why do those electrons move? What is the reason? Because we have to have some potential, all right? We have to have some electric potential. Remember we did the kind of ridiculous example where I said if I could separate out all these different charges, okay, then we would build up some amount of potential energy there. And remember, this is just like a battery, okay? A simplified version of a battery, but still a battery. Because we know that opposite charges are going to attract. So as soon as I put a connection between these two sides, they're going to want to recombine. Okay. Now, what if I had positive over here and positive over here? What do we know about like charges? They're going to repel. Okay. So it's only these like charges that are going to repel. Opposites are going to attract. Okay. And so we did a decent amount of work with this. Okay. We just did that Ohm's law and power law. Okay. What we need to talk about today, okay, we need to say, what if we have more than one electrical appliance? Okay. What if we have more than one light bulb hooked up? Okay. We already know what to do. I mean, just like our quiz today, if I have a 9-volt battery connected to a light bulb, okay, we know how to get the resistance, current, and voltage from Ohm's law and the power law, right? But now, what we can do to make our lives a little bit easier is instead of me drawing this crappy picture of a battery and a light bulb every time I want to talk about something like this, we're just going to draw a very simple circuit. All right? Now, a circuit is just going to be a way for us to represent an electrical system. Okay? And now, I think I mentioned this before, but if you were in instrumentation or something, you've probably seen things way, way more advanced than anything we're going to do here. The only thing we're going to worry about, all right, are resistors, basically a squiggly line, okay, and power supplies. Okay. So in this case, our light bulb here is our resistor, and this 9-volt power supply, or 9-volt battery is going to be our power supply. Okay? Because really, in a very simplified way, we can represent everything as resistors. All right? These lights right here turn on because they resist the flow of electrons. Okay? We can turn an electric motor because there's something in there that resists that flow of electrons. Okay? So we're going to represent everything as a resistor to begin with. Now, in a light bulb, it's easy to see this resistor because anyone ever looked at a really old light bulb? And what's in the middle of every light bulb? There's a filament, okay? There's a little coil of wire, okay? This is what's resisting the flow. But even something like this projector up here, okay? This projector probably has, I don't know, a few thousand resistors in it, okay? But overall, as a whole, it resists this flow of electrons, which allow it to do what it's doing, okay? And so we're just going to represent this with our power supply and our resistor, okay? But now, what if, I'm just going to go ahead and put this up here because I don't want to draw this out. Okay, what if we have more than one light bulb connected to a battery? Okay? Because, I mean, obviously in this room right now we have a bunch of lights on. All right, we have a bunch of things going on. Okay? And so there's really two ways that we can connect things, all right, together when we're talking about electrical systems. Now, the easiest, all right, is just a series. Okay? And a series circuit just means we're going to have our wiring go from one light bulb to another to another. Okay? If we look at this, this means that we have some resistance here, we have some resistance here, some resistance here. The current is traveling through this entire system, all right? And that each one of these has a different voltage. Okay? Now, before we even go any further, can you see one problem with this type of circuit? one goes out, the whole thing goes out. Okay? Because remember, to have electricity, we have to have this moving charge. Okay? So if this light bulb goes out, if I take this light bulb out, I don't have a path for these electrons to travel on anymore. Okay? If I don't have a path for these electrons to go anymore, all these other lights go out. Okay? Can anyone think of a good example of a series circuit? Christmas lights. Okay? You know, if you have one light go out, the whole strand goes out, because you've opened up that circuit. So if we want to represent this, all right, as a circuit, we can just say we have one light bulb, two light bulb, and three light bulb. Okay. Now the easy thing about a series circuit, all right, is that if we want to find the resistance of the whole thing, all right, if we want to know what the total resistance is, all we have to do are add up the individual resistances. So let's say this first light bulb has a resistance of 3 ohms. This second one's 5 ohms, okay, and this third one's 2 ohms. Let me go ahead and go to another page so we have a little bit more room here. So what we're saying here, all right, is that this first one resists the flow of electrons some amount, equal to 3 ohms. The second one resists it some amount, equal to 5 ohms. Third one resists it 2 ohms. So if I want to find the total or equivalent resistance of this entire circuit, okay, I'm just going to add up the individual resistances. Okay? And so it doesn't matter if I have 3, if I have 5, if I have 50. Okay? I'm just going to keep adding them up. So here I have 3 ohms plus 5 ohms plus 2 ohms. So 10 ohms. Okay? What this means as a whole, all right, this circuit resists the flow of electrons 10 ohms. All right? So if I were to create another circuit with just a 10 ohm resistor, all right, it would have the same current, the same voltage, the same power. All right? We're saying that 10 ohms is equivalent to a 3 ohm in series with a 5 ohm in series with a 2 ohm. Easy enough, right? We can do this. Now, obviously, since we already said if one goes out, then they all go out, that's kind of a problem. So the other type of circuit, which your book doesn't do a very good job showing a picture of, I don't think, all right, it's going to be a parallel circuit. Okay. In this circuit, instead of connecting end to end, what we've done is we've created 3 separate tracks, one for each of these light bulbs. All right. So if one light bulb goes out, we still have a path for these electrons to go to the other light bulb. We still have a path for this last one. Okay. So if I draw a circuit diagram of this, okay, I like to think it kind of looks like a step ladder. Okay. So once again, we can still see, all right, if one goes out, we still have a path for the other one. Okay. Same way with this guy here. Now, one thing all electrical systems have in common, okay, is that the electrons are always going to go where it's easiest. Okay. They're going to follow the path of least resistance. And this means in an electrical system like this, all right, for some of them it's going to be much easier to go through this 2 ohm resistor. But since we have this other path, there's going to be this branching off. Now this is, if we wanted to figure out exactly how much branched off, that's a little bit complex. But what we can say, all right, is that for this parallel circuit, 1 over the equivalent resistance is just equal to 1 over the individual resistors. Once again, all right, we can keep adding and adding, all right? Doesn't matter how many we have. And so we can do this though, right? So we can say that 1 over 2 ohms plus 1 over 4 ohms should equal 1 over our equivalent, or 1 over our total resistance. Now we could plug this into a calculator, but Wouldn't it be more fun just to do this by hand? Come on. What do we need to have to add fractions? Yeah, I gotta have our lowest common denominator, okay? So in this case, that's gonna be 4. So 1/2 is really just the same thing as 2/4, okay? So if we add these together, we get 3/4 ohms, okay? But now we're not done here, all right? Because 3/4 ohms is 1 over our equivalent, okay? So what we can do now is just flip it. Okay, because remember, if we do this one thing to one side, we can do the same thing to the other side. So if we flip this so it's the equivalent resistance over 1, do the same thing over here, we get 4/3 ohms. So 1.3 ohms. Easy enough, right? Okay, now I know you might have already learned a shortcut for how to do this when there's 2 resistors. Okay, but this method is going to work no matter how many we have. Okay, we just take the inverse and just add them together. Okay, why don't you guys try one of these for me? Okay, let's say this time instead of 2 we have 3. Okay, and I'm going to say I have a 1 ohm, a 5 ohm, and a 10 ohm. Okay, so remember 1 over the equivalent is just going to be 1 over the first one plus 1 over the second one, and just keep going. Give that a try. Even if you've seen this a million times before, at least write it out. Okay? You guys all done already, or are you stuck? What'd you get? Yeah, sounds about right. Okay, good. Okay, because we just have 1 over 10, right? Plus 1 over 1 plus 1 over 5. Okay, so 1 over 1 same as 10 over 10. 1 over 5, same thing as 2 over 10. So 1 over our equivalent will just be 13 over 10. And flip it. Good. All right. So we can do this. Now, for the most part, though, all right, normal circuits aren't going to be this simple. They're not just going to have series. They're not just going to have parallel. They're going to be some combination of the two. Okay? So let's take a look at this. let's say this is a 2 ohm, this is a 3 ohm, and this is a 9 ohm. Okay? So when we have a circuit like this, we need to see what is in series with what and what's parallel to what. Okay? So remember, series just means we're connected end to end. Okay? And parallel is that step ladder type thing. So what is in series to what here? Okay? So this 2 ohms is in series with this whole chunk here. Okay? So that means before we do this series part, we need to figure out what is the equivalent resistance of this piece right here. All right? So if we have, okay, a 3 ohm and a 9 ohm in parallel, we just do basically just what we've been doing. Okay? And so in this case, our lowest common denominator is 9. So we have 3 over 9. That's supposed to be a 9. Okay. So 1 over our equivalent resistance is just going to be 4 over 9 ohms. So our equivalent resistance of this parallel part is just going to be 9/4 or about 2.25 ohms. Okay. So now at this point in time, if we wanted to take the time, we could redraw this circuit and say, okay, we have a 2 ohm resistor here in series with a 2.25 ohm. Okay. So that has that same electrical properties. Well, now if we have it in series, I mean, what do? Just add them together. Okay. So we have 2 plus 2.25, so 4.25 ohms. Okay. Yeah. Okay. Because remember, when we do parallel, all right, we're saying 1 over our equivalent resistance, or 1 over our total resistance, is equal to 1 over each of the individual pieces. So in the end, when we get 4 over 9 ohms, that's equal to 1 over our equivalent. So we need to get this equivalent on top, okay? And so if we flip this and get basically the equivalent over 1, we have to do the same thing over here, so we get 9 over 4. All right? Any other questions about how we did this? All right. Why don't you guys try one of these for me? And this is going to be another example of the most difficult circuit you'll see in this class. Okay? So if you can do this, you're good. Give me a second to actually write it down. Let me know if you can't read my crappy handwriting too. So 2 ohm, 1 ohm, 5 ohm, 10 ohm, and a 2 ohm and a 6 ohm. Okay. Could have been drawn better. Okay. Think about what's in series with what and what's parallel to what. I'll give you a couple minutes to get this started. Okay, and then we'll walk through it. Looks reasonable. Well, I know I probably didn't give you enough time. Let's walk through this together. Okay? What's your easiest place to start here? Yeah. So we have this 2 and the 1 here in series, okay? So this is just the equivalent of 3 ohms, okay? Where'd you go next? Yeah, so if we go up here, we can say 1 over the equivalent of this part up here is just equal to 1 over 10 ohms plus 1 over 5 ohms, okay? And this is the same thing as 2 over 10. So that means we have 3 over 10 ohms. Yeah. So our equivalent of that part is just about 3.3 ohms. All right? We can probably do this part next, right? Yeah, so if we say 1 over our equivalent here is just equal to 1 over 6 ohms plus 1 over 2 ohms. So this is just the same thing as, yeah, 3 over 6. I know my handwriting's getting worse. So we have 4 over 6 ohms. So that comes out to be 6 over 4, which is about 1.5 ohms. All right. So what can I do next? Okay, well, we'll just add these two, right? Because basically I'm saying I have 3.3 ohms here, okay, and 1.5 ohms here. So that equivalent of that top part is just going to be 1.5 ohms plus 3.3 ohms. So about 4.8 ohms. Everyone with me so far? All right. What's my last step here? Not add though, right? Yeah. Because what I'm saying now is that I have a 4.8 ohm resistor up top here, okay, and a 3 ohm here. I'll just redraw this real quick, okay. So here's my 3 ohm, and here's my 4.8 ohm, okay. So now I have these guys in parallel. So what I need to do is just once again say 1 over my equivalent is equal to 1 over 4.8 ohms plus 1 over 3 ohms. Now, in this situation, all right, what? Well, in this situation, it'd probably just be easier to use a calculator. All right, I'm going to be quite honest with you. Because I don't want to do that. All right, so here we can just say 1 divided by 4.8 plus 1 divided by 3. Anyone with the calculator want to help me out with that? What? Okay, well, what do you get before that? Oh, come on, someone help me out. All right, we could do this to, so 1 divided by 4.8, that's about 0.2 plus 0.3. So, yeah, we'll say 0.5, all right? Okay, but now we're saying 0.5 is equal to 1 over our equivalent. So we basically need to take 1 over 0.5, all right? So our equivalent is just going to be 1 over 0.5, which is going to be around 2 ohms. Whew. All right. Now this is a mess, all right? Anyone have a question about what we did here? Okay, good. And so remember, I mean, this is the most difficult we're going to get in this class. Okay? So it means if you can do this, all right, you'll be good on anything for the test from next week. Okay? Now, with our last couple minutes, all right, we need to talk about a few more concepts. Okay? And then I promise we'll be done. We can skip safety features. We don't care about safety. All right. But now we've talked about electricity so far. But remember the title of this chapter was Electricity and Magnetism. Okay. Now what we're saying here is that when we talk about electricity and magnetism, we can't have one without the other. All right? You're always going to have, if you have magnetism, you're going to have electricity, and if you have magnetism, if you're going to have electricity, you're going to have magnetism. Okay? But now what do we know already about magnets? Well, yeah, opposites attract, right? But instead of having positive and negative as we do in electricity, okay, we're going to have a north and a south. Okay? Okay? But you're right, just like electricity, okay, if I have another magnet over here, okay, it's a north and a south, they're going to attract, all right, because these opposite poles are going to attract. At the same time, if I flip this around, all right, so that I have two souths next to each other, there's going to be this repulsion, all right. Good, all right, easy enough. Where do magnets come from? How do you make something a magnet? Okay. There's a couple ways, right? That electricity is one way, but what's an easier way? Let's think about something for a second. What, if I had a magnet in this room right now, what would it stick to in this room? Certain types of metal though, right? Not all metal, okay? It'll stick to iron basically, right? Okay? Well, certain types of metal, all right, due to their properties, all right, due to their electrical makeup, are really going to be composed of tiny individual magnets. Okay? So just like we saw, okay, how in all of us there's all these positive and negatives, okay? And really, in certain metals, all right, there's all sorts of tiny little magnets, all right, with their north and south just randomly oriented, okay? What do you think would happen if I brought a big magnet close to this one? All the norths are going to go to that side, okay? Because what we know is that this south end, all those north parts are going to be attracted to it. All right? So if I can redraw this, this is when it probably should have been better to have animation here. Okay? All these norths are going to line up now. Okay? So that essentially what I've done here is created a magnet. Okay? I've made a magnet from all these individual parts. And really, all right, in a normal magnet, this is the same way. We see the north and south ends, but it's composed of these individual regions. Because what do you think would happen if I cut this magnet in half? We'd still have two pieces with north and south, right? We wouldn't have just one north and one south, all right? Because it doesn't matter how many times you cut this up, we're still going to have this north and south, all right? Now the same way, all right? If I say you can't have electricity without magnetism, can't have magnetism without electricity, if I ran a coil of wire through this, all right, pumped a bunch of electricity through it, I could get this same reaction. What is this an example of? You probably don't see this every day, but where do you see electricity used to create a magnet? Junkyards, right? Okay. That's just what an electromagnet is, those giant magnets they use to pick up cars and other stuff, all right? We're using electricity here to align all these individual parts so that we have a magnet. Now, what happens the second you take this magnet away here? This one goes away. Second you take away this electricity, you don't have a magnet anymore, okay? So we're going to spend some more time on this on Monday. Because remember, Monday is going to be our last bit of new material before the test next week. Okay? You should be able to do these homeworks now. Okay? And talk to me if you do have any questions before the test. See you on Monday. Oh, no problem. Hope to see you again, maybe next year, right? What? Week from today.